hypothesis testing of the population proportion using a binomial distribution. According to a genetic theory, 45% of plants of a certain species should have red flowers. So the proportion P is 0.45. In a random sample, and the sample size here is 12, 3 had red flowers. So 3 is the test value. We're using a 10% level of significance, and we're just testing the theory. So this is a two-tailed test because we're looking for a change from the 45%. Starting with the critical values method, the sample size is 12. The test statistic is 3. The proportion is 45%, so 0.45. And we're looking for a change. So the null hypothesis, the no change hypothesis, the proportion is 0.45. The alternative hypothesis is that there is a change. So the binomial distribution, n is 12 and p is 0.45. Our significance level is 10%. Because this is a two-tailed test, we need to split this. So looking at the x values here, 2 of these are needed for our critical values. For a two-tailed test, we have 2 critical values. So one will be up here somewhere, one will be down here. So the lower tail up here and the upper tail down here. The lower tail is easier, so let's take the 5% and we'll go down these probabilities here. Anything below 5% will be in the critical region, so these 3 here. So this will be our critical value. 2 is the critical value. If you go to the next one, this probability is above 5%. So are all of these, so they don't count. So for the lower tail, 2 will be the critical value. Now for the upper tail, we start off with 5% or 0.05, do 1 minus that probability to get 0.95, and then going down the tables, we're looking for a probability which will be at least 0.95, the first one, which is this. And 8 is not the critical value, it's the next one along, 9. So we have 0, 1 and 2 in this critical region, and we have 9, 10, 11 and 12 in this critical region. So we reject H0 here, we reject H0 here, and we accept H0 in the center. And the acceptance region is from 3 up to and including the 8. So this is the acceptance region. Our test statistic is 3. Clearly that falls in the acceptance region, so we're going to accept H0 and conclude that there is no significant evidence of a change in the population proportion of red flowers. And we need to show some evidence why we've selected 2 and 9 as our critical values. So this region, the critical region here, px less than or equal to 2 has this probability, and this is within the 5% for the split significance level, and so is this. This critical region, px more than or equal to 9, has this probability. So if you do 1 minus less than or equal to 8, you get this. And this probability is also within the 5% split significance level. And because we've accepted H0, it's possible that a type 2 error was made, and the type 2 error can be calculated using some new value of P and the acceptance region. So in this context, the probability of a type 2 error is the probability that x is between 3 and 8 inclusive, given some new value of P. Moving on to the probabilities method for doing the hypothesis test. So we have our sample size, our test value H0, H1, the binomial distribution. We split the significance level because of the two-tailed test. The test value is 3. We can calculate two probabilities, the probability that x is less than or equal to 3, and compare that with the significance level here, the 5%, and we can calculate the probability that x is more than or equal to 3, and again compare the probability with the 5% here. So looking at both calculated probabilities, they are both more than 5%, so we're going to accept H0. If this was less than 5%, or if the probability here was less than 5%, then we would reject H0. And it's 5% that we're comparing each one of these with. We're not using 10%. We've split the 10% into 5 and 5, so we compare this, the lower tail, with 5%, and this, the upper tail, with 5%. And as we have not calculated any critical values or acceptance and rejection regions, we can't go on to work out the probability of errors. To calculate errors, use the critical values method.